Okay, so I kind of wanted to, it's great to be here. Well, see everybody's getting older and grayer, including me. At least you're still here, I guess. Yeah, I just realized it's 28 years since I started ICSI. As I go back doing this. So I want to talk about a little is the work we did at ICSI on neural net hardware, accelerating neural nets. And I think it's funny because right now this is the hottest topic is AI hardware. So we were kind of a little too early. I want to dive and talk about that and what we did then and how it relates to what's happening now. So I've been giving this talk a lot lately, and so I go back and look at, there's actually been, as far as I can tell, 3 big waves of interest in neural nets. And the first one was in the 50s and 60s with perceptrons. This is really the first wave of doing this. Then we had the 80s, 90s, which was basically backprop and 2 or 3 layers, and that's kind of the ICSI, the part of ICSI history I was involved in. And then in 2010s, it's this deep neural networks, which deep just means more than 3, as far as I can tell. So I think one thing, people who've been working in this field realize all these ideas were kind of known way before they became popular and applied, but this is when they really became, part of the popular development. So single layer perceptrons, I like going back and looking at this machine. This is Rosenblatt. He actually built this perceptron, which was an analog computer. What was great about this was it had a potentiometer for each weight. So each weight in this neural network was a real-life potentiometer. And what was really cool, this machine had training. So the way they did training, there was electric motor on each potentiometer. So you could electrically turn the weights. But it was only a single layer machine. And back then people realized theoretically, there's a lot of stuff you couldn't do with a single layer perceptron, including learning the XOR function was a classic example. Now what's interesting to me is at the time, people realized that multiple layers could do more. They just, for some reason, that meme propagated and people got less interested. And the whole field moved on to symbolic approaches in AI around that time, and there was a lot of work. There was a 5th generation computers, Prolog, Lisp. They were going to be the future of AI. Of course, that didn't actually happen. AI is a bit harder than that. But then the second wave of neural nets was really the rediscovery of backprop and finding out how to train 2 and 3 layer networks. I remember these books came out, the parallel distributed processing books. I think ICSI was really founded on the wave of this interest in structured connectionist networks in the late 80s. I remember these books being very exciting. And I think what's interesting is to read through my summary of what people thought back then and how it reads exactly the same right now. Just substitute 2 for more than 3. So these trained networks do surprisingly well at many hard tasks, things that people thought were hard. You could just, without knowing much, you could just throw a net at it and you got good results. Experts will complain the results were unexplainable. You can't use this thing, I don't know why it's working. Obviously that makes me less valuable. I mean, that's why they're complaining. The training was extremely slow, so people were motivated to go build custom hardware. So at ICSI, Morgan, there's a very as well in this classic picture, they were experimenting with these big neural networks for speech recognition. And, Morgan used to call these big dumb nets, right? And this was way back in the day, but they needed faster hardware to build these. So they used the most effective in terms of flops per dollar chips you could get, which were these new DSPs that had just come out from Texas Instruments, these floating point DSPs. And then they wired together with an FPGA that provided systolic communication between those DSPs. And so Jim, back there, he designed these boards. They work very well. A lot of software written by various people. Phil Cohn, Jeff Bilms, other people worked on the software for this. So this was a very fast, flexible machine, but it was very expensive. It's like hundreds of thousands of dollars in those dollars, which were real dollars, right? So, but compared to a workstation at the time, it was like 200 times faster to do training on this system. So this was why Morgan and his team had built this back then, enabled them to do research they couldn't have done otherwise. So I joined Berkeley as a naive grad student back in '89, and Morgan I was taking the VLSI class, and Morgan came to the class to tell about the work he was doing at ICSI to recruit students to go work on VLSI for neural nets. So I was a young, naive grad student. It's me about that time. So I come to see Morgan, and he's like, well, we have this real cool neural net architecture, but we need custom silicon to make it work. So we had this unary encoded, reduced precision network, and we were going to put this into all these devices, and we needed some cheap silicon to do this. So I developed this thing called HipNet, which was just a early customized neural net inference engine, and we started building it. What was cool at the time was Moses had this program where for $500 you could design a custom chip, have it made, get 40 samples, It was only 2-micron CMOS, but this was very cool. We got a lot of experience building these chips. This was great, how we learned how to do silicon. So we start off building all the different pieces of this customized neural network chip. We're having a great time, learning a lot, building a team. It's a lot of fun. Meanwhile, the speech guys kept innovating, and there's Morgan again. And he's like, there's this even cooler neural net architecture for which we need custom silicon. And it doesn't look anything like the old one. Can you build a different chip? And so we're like, okay. So, what's it? Fool me once. So we're like, okay, we don't trust you guys to fix on any architecture. So instead of building custom silicon, we're going to make a programmable architecture. So then we started designing a programmable architecture. So I sort of sat down, looked around, and came up with this thing, which was a VLIW SIMD machine. And this was a very big architecture for the time. You got to think back to what would fit on a chip. And so we started building this thing, which had a big long VLIW control word and a bunch of parallel ALUs in it and a scale unit. I remember there was a grant application where some accountant complained about our use of a very long instruction word. They said, couldn't you get by with just a long instruction word? This was from an accountant's view of architecture. Anyway, they were probably right, actually, so as it turns out. So we actually built a test chip. This was a sub-piece of this SIMD array. We actually built this test chip in bleeding edge 1.2 micron CMOS. It ran at 50 megahertz. Actually, it worked very well. I remember Thomas Schwer was one of the visitors. He helped us test this out in 1992. So we were very far along in developing this architecture based on this VLIW SIMD machine. But at the same time, what was going on was we were getting more ambitious. So at ICSI, a much larger group had put together a proposal to build a connectionist network supercomputer. We really felt that to advance the state of art of neural networks, we needed a huge machine that could do a lot of compute. So we came up with this design. Here is the drawing of it. You should have seen the styrofoam model, which was even more impressive. And Jim put together this whole CNS design, but it had a lot of processors connected in ring mesh with I/O, and we made sure the wires wouldn't go through the fan at the bottom. That was Dave Patterson's comment on this. We should make sure we don't route the wires through the fan. We took his advice. And this is the group at the time. So this is the great thing about CNS was a big collaboration all the way through the stack, from neural network applications to libraries, the language piece either, the architecture, silicon, putting wires through the fans. Everybody worked together on this big thing. So look at these names. There's me, Brian Kingsbury, John Mosnick, Bertrand Nirasu, Jonathan Bacharach. I think that's David Stoudemire. Is that? Yes. Yep. Sitting next to him, I'm blanking, Carlos Acan, John Lazaro, Jerry, and Morgan. I forget the gentleman in the middle. Anybody remember? No, okay. So it was a big group, and it was a very multidisciplinary group, which I think was one of the big strengths. But because he wanted this bigger machine, already started in the small machine, realized that even though we'd made a lot of progress, almost finished this VLIW machine, we actually abandoned it. And the reason was, having designed this VLIW machine, I then had to write the test code for it. And it was so painful, and it just took forever, and I realized there's no way this would work for this CNS machine as well, so we wanted to do something different. Basically with the understanding now, this machine was going to have to support a lot of software. It wasn't just going to be running a few loops, it's going to be running the whole system. So we abandoned this Bird VLIW very late in development, or what we thought was late in development. We thought we were almost done, we were probably another year away. But we scrapped it and then decided to go build a different kind of machine, which is a vector microprocessor. So this was T0, this was my thesis project. This was the first single chip vector microprocessor. So the idea was really, the crazed supercomputer idea was really good. Why not just take that and put it on a single chip? And that was basically what T0 was, with a goal of improving speed in neural network training. So we started with a MIPS scalar processor, added this vector coprocessor, put it all on one chip, and optimized it for neural networks. So this is an interesting part of the story, in hindsight, was we were choosing which processor to build this around. And at the time, there was a lot of standard risks out there. There was Spark, HP Precision, PowerPC, and Alpha. All of these are effectively dead now. Power is kind of on its last legs, but most of the ones are dead. MIPS we chose, and MIPS is pretty much dead now, because it was the simplest, had good software tools, and you could get Unix development environments. Also, MIPS had a 64-bit path, which we thought might be useful going forward. But then we went to look, should we buy or build a MIPS core? This is a standard component. We're using it to get access to standard software. So we went to talk to MIPS. And they said, we said we'd like to build a MIPS core. And they said, sure, great. It'll cost you $2 million. We're like, what do we get for that? Well, what you get is some test vectors and their blessing, right? So here you go, $2 million. You're now allowed to go build a MIPS core. And we said, thank you very much. No, we'll do something else. So came back to the ranch, and we're like, okay, we just build a MIPS core anyway, and we'll leave out the few instructions they had patents on. So they couldn't come after us and sue us, and just built basically a MIPS core that didn't have the patented features. Just build it ourselves. Now, one of the things we realized, the reason MIPS, like these days, you go to ARM, and they'd give you a soft core that you would use in your design. At that time, there weren't any soft cores. There wasn't really Verilog or any way to express the soft cores as a standard at the time. And so this industry, Verilog was just starting to appear at that time. So everything we did, we actually built this machine with schematics, not with Verilog. So we decided to build our own core, add everything ourselves on the side, and went ahead. So it was very successful. We built this thing. It's me and Brian, who was one of the main VLSI designers. So me, Brian, and Bertrand were the main people who built the chip. This is a photograph of the wafer. This is in 1 micron CMOS. It was fabricated by HP when Hewlett-Packard still had their own fabs a long time ago. So we built this. This was designed to plug into a researcher's workstation, the back of a Spark station. And this actually worked pretty well. We got significantly faster training than you could with your own workstation, even compared to like an IBM RS6000. That was like a $100,000 server, high-end IBM machine. But these things were way powerful. We built a bunch of boards. We shipped them to 8 sites, 9 sites. And the thing that always impressed me was that the last time somebody used this in anger, I think, was Arlo recently, in like 2004, which was way, there's no way you should be using a 40 megahertz, 1 micron chip in 2004, but I guess we'd written all this software. The other thing we'd done is parallelize the code. And so this is another thing we did back then with Phil Faber, who was a visitor from Switzerland. I think he came and worked on parallel training across multiple D0s to get higher throughput. Anyway, so we weren't the only people building neural network acceleration hardware. The Siemens, Uli Radmacher's group, had built this machine called Synapse, which was a big systolic array they'd used for neural net training. We brought that into ICSI and found out it couldn't do one of the activation functions we had, so it's basically useless to us. Anyway, so I'm going to fast forward. So what happened to all these 90s neural computers? There was this big wave of stuff. There was no market. Neural networks faded popularity. Other statistical methods became popular. And Moore's law really favored general-purpose processors. So this is kind of the chart that explains why they disappeared. We were developing right at the start of the hottest period of Moore's law scaling. So you couldn't really compete with general-purpose processors. And why you're seeing everything now is general-purpose processor scaling has stopped. Only a couple % per year performance improvement from your Intel cores, whereas in the old days, it was like 50% per year, right? So the old days, it made sense just not to do special things, just use a general curve. Now it's really slowed down. So everybody's building stuff. NVIDIA got kind of lucky. They built these GPUs to do graphics, and they found out they're okay at doing neural network training, and this is now the dominant thing. But they weren't really that efficient, so now people are building custom AI chips, including Google, who's put out a whole range of chips where they built these custom chips. Give you some idea how important neural net training is to Google. The TP3, TPU version 3, is the first time Google has put water cooling in their data centers. And they did it basically because they really wanted this higher performance. So they've packed the cores together, they need water cooling. The first time they've done it. So, this hardware is important. Now, one thing I find funny is, this is less full reticle with reduced precision vector processing at high bandwidth local memory. I'd attach a bunch to a server to accelerate neural network training. It's kind of what we did, but this is about 100 AI hardware startup pitches right now that I've seen. It's basically almost identical. So just quickly to end up, so where I kind of went along with this, we did a bunch of other work. But this thing about needing to get access to a core to build things around, that's kind of led indirectly to this RISC-V project, which is an open source, an open standard ISA that we developed at Berkeley. And we found people started using this. It's a license-free, royalty-free ISA, anybody can go use. And we created this nonprofit RISC-V Foundation to drive it. I'm going to quickly go through this timeline. But from starting out in Berkeley back in 2010, this thing has now taken off. I incorporated this foundation to manage this standard as a standard. But like a couple of years ago, NVIDIA announced all the future GPUs are going to use RISC-V as the basis of their control cores on all their future GPUs. And last year, Western Digital announced all their future products are going to be based on RISC-V. And across the industry, there's been a huge uptake of this idea of having a free instruction set processor. So I did the startup Sci-Fi with a couple of my grad students. We've been putting out the first commercial silicon based on this. But this thing is really taking off. We have, in the foundation, there's over 180 members, including most of the biggest semiconductor companies in the world, like Google, Samsung, Huawei, NVIDIA, Qualcomm, Rambus, Microsemi, Mellanox. Like all these people are actually doing serious stuff with RISC-V. The Indian government has picked it as the national ISA of India. I'm working with the Chinese government, and we'll see where that goes. But the growth history has been phenomenal. This idea has really taken hold that you can have a free ISA, they can build their own things around. So the other thing about RISC-V is I kept working on vectors this whole time. So RISC-V has a vector extension. We kind of joke about it's RISC-V, but that V really stands for vectors. But one thing we're doing is adding 2D vector extensions, which are really designed to do well on the kind of matrix multiply convolution operations that are really at the heart of all these AI accelerators. So there's a big interest right now in that. There's a lot of those startups that are actually using RISC-V to build their AI hardware. So to conclude there and just say, you know, this is kind of led directly, I think, from that research experiences here at ICSI. It was a great time, great fun building this stuff up, and still having a lot of fun building chips and vector machines. So there you go.